Okay, I'm started recording again. So the next half of the section of this lecture, we will discuss the application of the Newton-Raphson power flow method for this three-bus power system network. We know this network very well because this is a network that we used to model it in the MATLAB. Your bus one have a slack generator, which is having a 100 MVA base, and the voltage of this bus is 25 kV. But the initialization of the load flow, we assume the voltage is 1.05, angle of 0 degree, and then your bus 2 having a load which is having 400 megawatt and 200 megawatt, and bus 3 which is a generator bus, and which having a constant power of 200 megawatt delivering to the network, and the V3, the voltage of the bus 3 is defined as 1.04 per unit, and the line impedances for all the lines, line 1 2, line 1 3, and line 2 3 are given in this line impedance. Here resistance and reactance are given in per unit. So now we have to solve this network by the initialization value that is given in the network diagram by using Newton-Raphson load flow method. Next slide. Before we solving the network Newton-Raphson, because some softwares that needed some values must be converted into per unit to actual, and because the parameter configuration in the softwares which needed, some of the softwares they needed the data in per unit, and some of the software they need the data in actual value. So irrespective of the software platform we're going to use, so we also need to understand how you changing the per unit to actual value and vice versa. So in this case, example, the zone 1, which is the bus 1, which is 25 kV, and we assuming the base MVA for the whole power system is 100 MVA. So the zone 1, that is generator 1, the slack generator connected in bus 1, which is 25 kV, and the zone MVA for the whole power system 100 MVA. So the formula to calculate the zone impedance, VB squared SB. So the VB is the zone 1, which is a bus 1 voltage 25 kV. 25 into 10 power 3 is a 25 kV square divided by 100 MVA, 100 into 10 power 6. So this value will come to 6.25, which is the base impedance. Then our line resistance and reactance. The line resistance for line 1, 2 is a given data from the SLD from the previous slide is given 0.02. What do you mean this? Why it is squared? Oh, this one. Because the formula, if you look at the base impedance, VB squared by SB. So the formula is VB squared. The zone impedance formula is VB squared by SB. So this square is part of the formula. I'm not sure if it's clear. Someone asked me why it is squared. I assuming you asking the square for the VB squared. Is it clear? Okay. So because the formula is VB squared by SB, so VB squared divided by SB. But there is a separate derivation how we come to the formula VB squared SB, but that is not important here. But the formula will be given in the formula sheet, and based on that we can see the zone impedance is VB squared by SB. So the line impedance 1 by 2, line 1 2, we say the resistance is given in 0.02. So what we're doing is in per unit. So we want to convert that value into actual. So what you're doing is you multiply by the base impedance. So 0.02 times of the base impedance, we calculated 6.25. So it's giving 0.125 ohm. And then the reactance formula we know XL equal to 2 pi FL. But in MATLAB software, specifically, if you look at, we need an inductance. So in order to derive the inductance, you rearrange this formula, L is equal to XL divided by 2 pi F, where XL is a line reactance and it is given 0.04. So what you're doing is, this 0.04 is in per unit. So we want to convert them into actual value. So multiply by 6.25, and the denominator is 2 pi f. We know our frequency for the power system we assumed as 50 Hz frequency system. So 2 pi f is a constant. So you substitute that value and be able to calculate what is the inductance for for line 1, 2. The same procedure will be applied to calculating the resistance and inductance of line 1, 3, and the same thing is used for line 2, 3 as well, your resistance and inductance. And then the next thing is, if you notice the SLD diagram in the previous slide, your real and reactive powers, they given in actual value. So we have to convert them in per unit. For example, your generator bus, which is bus 3, which is constantly supplying 200 megawatt to the power system. So if you want to know the 200 megawatt, which is equivalent to per unit value, you divided by the apparent power, that is a base we are assuming as 100 MVA, as I mentioned here. So 200 by 100, which gives you 2 per unit. And for the bus 2, which is a load bus, and from the load bus, we know the real power is 400 megawatt and reactive power is 250 megawatt. So again, we dividing the base MVA of 100. So we getting our load per unit, real power is 4 per unit and reactive power 2.5 per unit. But you remember you did ask these questions last time, but just want to quickly remind on that why I'm dividing my apparent power, because the real power divided by real power in order to get the per unit. But my assumption is I'm assuming the apparent power 100 MVA, but in that case I'm assuming the power factor is a unity power factor. But in case if the is not a unity power factor, then in that case it might not be with, for example, is 0.9697. So it means the base MVA that you're looking at is not 100. It could be slightly less than 100, maybe 96 MVA, 97 MVA. By the assumption here, what I did is I'm assuming the power factor, unity power factor, so that I dividing as a base power of 100 MVA, and I able to get your my generator 3 2 per unit, and load real and reactive power is 4 per unit and 2.5 per unit. Is it clear? Okay, next slide. It is a procedure to draw the impedance diagram, and in the impedance diagram we have to represent the source impedance by XL, and then the transmission line impedances, and if you have any loads that is connected, motor, etc., we have to represent that impedance as well. But as I mentioned few occasions, you didn't learn a per unit system and the impedance diagram as part of the per unit system. So I have a separate section to teach you the per unit system and also the impedance diagram for the per unit system. So for now, we can skip this step, but I think I have notes on per unit system and the impedance diagram to draw the based on the per unit system. It is part of chapter 7, and the chapter 7 notes is already uploaded in the Blackboard for you yesterday. So hopefully by next week we will able to teach the per unit system chapter 7. So we will be better understanding of what is the purpose of the impedance diagram. And the next step of this network as part of the Newton-Raphson power flow, the first step, as I mentioned, we have to determine our Y-bus matrix, and it is admittance matrix. But remember, this is an example that we discussed how we formulated the Y-bus equation for the 3-bus system. But this network system is the similar 3-bus system what we given the actual network also. So based on that, we have the formula for the 3-bus system. This is a formula that we derived earlier today in the morning section. We discussed about how we derive the Y-bus admittance matrix for the 3-bus system. It is given here. So what we can do is we can able to apply this formula and to calculate all the elements of the Y-bus matrices, all the elements of the Y-bus matrix. For example, Y11, so we have Y11 equal to Y11 plus Y12 plus Y13. But in that case, it means 1 is a self-admittance. The self-admittance in this case is not given. So we only have Y12 and Y13. Y12 is this one, 0.02 plus 0.04. So we taking that value, and then y13 is between connection bus between 1 and 3 is this for this line, which is 0.01 and 0.03. So you can see 0.1003. So we able to calculate this value and we can get it 20 minus j50. Okay. And the other thing also, you notice it, because it's a y, the values is given as is impedance. Because of is given in impedance, we have to take a reciprocal, the reciprocal of the impedance equal to admittance, because we have to write it down in terms of admittance. That's why the minus sign, is a minus is not minus 1, is power minus 1. It means we're taking an inverse of the impedance value in order to calculate the admittance value. The same procedure applied to y12. Y12 is a negative sign of minus y12. So 12 is this line between 0.02 plus 0.04. You can see 0.02 plus 0.04. So is the inverse, is a negative sign is there. So inverse of this one will become minus 10 plus 20j. So by repeating these steps, by using these formulas, we should finally able to calculate all the elements of the Y-bus matrix. And in your right hand side, I have given the Y-bus matrix, which we have calculated the steps in the first section of this slide. And then this values is given in rectangular form. But remember, when I spoke, when you're applying a Newton-Raphson method, we have to use it in a polar form. So polar form, we converting this rectangular form into a polar form, and the same equation, that is y bus, is written here in a polar form. Here highlighting, this is what the y bus is written in a polar form, which is equivalent to the rectangular form here in the above. So in general form, we do know the rectangular form, which is yik, which is a magnitude, of the admittance, and theta ik, which is a phase angle of the admittance. And sometimes, but in this case is given in a degree, but sometimes if the angle is in a radian, so we have to convert the radian to degree, but the equivalent formula is 1 radians is equal to 57.29 degree, or otherwise we can say radian times of 180 divided by pi will give in a values in degree. But fortunately, I already made it here all the angles in degree. So, but this is just for noting purpose. In case if it is in radian, we have to multiply by 59.26. How the 59 is coming? Because 180 divided by pi, which is giving 59.26. All right. So the first step of the Newton-Raphson load flow method is taking the given power system network and formulating the Y bus, and writing the Y bus matrix into a polar form. That is the first step. Any questions from the Y bus formation? If not, I move on. So now initialization of the load flow. The initialization of the load flow, as we know, the slack bus, there will be a 2 parameters is given, which is the phase angle and voltage. In that case, if you remember what is the phase angle and voltage, I think it's 1.05. If I go back to the SLD again, couple of slides. Yeah, you can see 1.05 angle of 0 degree, that is your V1 and delta 1, and then the V3 is 1.04. Yeah, that based on that, this initialization is given here. So in this case, the slack bus, we have to the given parameters is V and delta. There are only 4 parameters for every bus that is assumed in the power system network that is given. For slack bus, V and delta is given, but the parameters to be calculated is P and Q. It means we don't know what is the amount of real and reactive power the slack bus need to generate in order to maintain the voltage regulations and the stability of the system. For generator bus, it is called as a PV bus or generator bus. So P and V will be defined, and the other 2 parameters, which is the reactive power and phase angle, will be determined at the end of the load flow. And for the load bus, we need to initialize your P and Q. It means 400 megawatt and 250 megawatt power is the initialization. And at the end of the load flow, we need to determine what is the voltage and phase angle for that load bus. So in simplicity, by speaking about this table, for slack, the power system only have 3 buses: slack bus, generator bus, and load bus. And in the typical example, we consider bus 1 is a slack bus 2 is a load bus, and bus 3 is the generator bus. And these are the given parameters for the slack bus, generator, and load bus. And these are the unknown parameters that need to be calculated for all the 3 buses. By keeping in this initialization, we will go on to solve our system. So in that case, you can see the same table is repeated, column 1, column 2, column 3 is the same as it is from the above. And what I'm trying to highlight here is we need to find out, because for each case we have to find out your P and Q. For example, in this case, the given parameters is V1 and delta 1. For slack bus, we're not taking any appropriation, so we leave it. For the load bus, what you're doing is we need to take the appropriation, which is your V2 and delta 2. It means we have to partial derivation P2 P2 versus V2 and Q2 versus delta 2. And for the voltage bus or the PV bus, is a PV bus, that's why P and V. Bus 3 is a PV bus, so P3, V3. So in this case, your delta must be calculated. So what you're doing is we have to partial derivation again your P3 versus delta 3 and V3 versus delta 3. Can I attend to this call because someone is here quickly? Give me 1 minute, 2 minutes, I'll back in 5 minutes.